Ever needed to compare the averages of, say, 3, 4, or even more groups all at once? Well, if you have, you've definitely come to the right place. Today, we're going to pull back the curtain on ANOVA, a super powerful statistical tool designed for exactly that job. To get our heads around this, let's start with a question I think we can all relate to. How much does pulling an all-nighter actually slow you down? It's a question researchers have looked at, and it gives us the perfect real-world scenario to see what ANOVA can do. So here's the actual data from a study. You've got 4 groups of people, with their reaction times measured after 12, 24, 36, and a whopping 48 hours without sleep. Now, just by glancing at the average for each group at the bottom, you can see a pretty clear trend, right? The longer people go without sleep, the slower they get. But here's the big question. Is this trend real, or is it just a fluke? Because, just eyeballing a trend on a chart isn't really enough. We need a specific tool, a rigorous method, to tell us if what we're seeing is a genuine effect or just random noise. And that tool has to answer this one crucial question. Are the differences we see statistically significant? In other words, how can we be sure that the sleep deprivation is what's really causing the change and not just some random luck in who we happen to test? Now, if we only had 2 groups, like just the 12-hour and 24-hour folks, we could use a simple t-test. Easy enough. But we've got 4 groups. We need a bigger tool for a bigger job. And that's exactly where ANOVA comes in. It lets us ask a much broader question. Is there any kind of significant difference happening somewhere among all of these groups? So let's put a formal name to it, ANOVA, which stands for Analysis of Variance. Its whole job, its entire reason for being, is to look at the means of 2 or more groups and tell us, hey, are the differences you're seeing legit or not? Okay, now the name analysis of variance can feel a little weird, right? Because we're testing the difference between means. So to really get what's going on, we're going to look at ANOVA from 2 totally different but equally powerful angles. All right, first up is what's called the structural model. The best way to think about this is like a recipe, a mathematical recipe for every single data point in our entire study. The recipe says that any one person's reaction time, their score, is made up of 3 ingredients. First, there's the grand mean, which is like the baseline average for everybody. Then you add the group effect. That's the special sauce, the little bump up or down you get just from being in, say, the super sleep-deprived group. And finally, there's some individual error, which is really just the random noise that makes everyone a little different. Now that middle part, that group effect, that's the one we really care about. You see, when we run an ANOVA, what we're really testing is whether that group effect is even real. Our starting assumption, what we call the null hypothesis, is that all those group effects are 0, that being sleep-deprived actually has no impact at all. The test's job is to see if our data gives us enough evidence to stand up and say, nope, that assumption is wrong. Okay, that was the mathy way of looking at it. Now for perspective number 2, which is much more visual and, for a lot of people, way more intuitive. This one is all about breaking down the variation in our data. And here's the big idea, the one that gives ANOVA its name. It takes all the wiggles and jiggles in our reaction time data, the total variation, and it neatly splits it into 2 distinct piles. One pile is the variation that happens between the different sleep groups, and the other pile is the random variation that happens within each of those groups. And this is the perfect way to picture it. Think of the total variation as a whole pie. ANOVA comes along and slices that pie into 2 pieces. One piece is the variation we can explain by knowing which group a person was in. That's the variation between groups. The other piece is all the stuff we can't explain, the random noise. That's the variation within the groups. So we've sliced up our variance pie. So what? Well, this is where the magic really happens. This simple split sets up a brilliant final test, a showdown between the signal and the noise. This brings us right to the heart of the whole thing. How does ANOVA actually make the call? How does it decide if the group means are different enough to matter? It all comes down to something called the F test, or the F ratio, and it's so incredibly elegant. It's just the variation between the groups divided by the variation within the groups. That's it. It's a simple ratio of the potential signal to the background noise. Now, to make this whole signal versus noise idea crystal clear, the source material gives us this absolutely fantastic analogy. Forget statistics for a second. Imagine you're at home and you're worried you might have a gas leak. Okay, follow me on this. The variation between groups, that's like the air inside your house. It's got the normal background air plus maybe a signal, the gas leak.
Now, the variation within groups, that's like the air outside your house. It's just the background noise, the normal air quality. So the F-test, it just compares the air inside to the air outside. And if that ratio is huge, if the air inside is way, way different from the air outside, you've probably found a leak. You've found a real effect.
So when you boil it all down, all the F-test is really asking is one simple, powerful question. Is the signal we're looking for significantly louder than the random noise that's naturally in the data?
Okay, theory time is over. Let's bring it all back to our sleep deprivation study and see what the F-test actually told us.
This right here is the ANOVA source table, the final output. And look, you can see our pie slices right there. The total variation, or sum of squares, is split into between groups and within groups. But the number you really want to look at is that F ratio. Wow, it's 46.5. That's a huge number. It's telling us that our signal, the effect of sleep deprivation, is over 46 times stronger than the random background noise. And a huge F ratio like that gives us a tiny F probability, or p-value. In this case, it's pretty much 0. This means the probability of seeing a difference this big, purely by chance, is virtually impossible. We can confidently reject that null hypothesis. So what's the verdict? Well, we can say with a whole lot of confidence that sleep deprivation has a real, statistically significant effect on reaction time. The differences we saw are not just a random fluke. But, and this is a really important but, there's one final catch. You see, the F-test is what's known as an omnibus test. Think of it like a fire alarm. The alarm goes off, telling you there's a fire somewhere in the building, but it doesn't tell you which room it's in. ANOVA tells us that a significant difference exists somewhere among our 4 groups, but it doesn't tell us where. Is 48 hours different from 36? Is 24 different from 12? To answer those more specific questions, we need to move on to another set of tests, which leaves us asking, what's next?